converting between Fisher and Haworth projections. So we'll start off, we've got an aldose, and in this case, most aldoses tend to form six-membered rings, the Pyranos type ring. So in order to do that, basically the bond between carbons 2 and 3 is going to become the bond at the bottom. So our final structure is going to look something like this, and this will be the bond, this will be carbon 2, and this will be carbon 3. So that's going to be the bond that's at the bottom. So what we're going to do is we're going to rotate this 90 degrees. And as a result, we will end up with there's carbon 5, 4, 3, 2, and here's carbon 1. So now everything that was on the right-hand side is going to end up down. So we'll have hydroxyl here, hydroxyl there, and hydroxyl there. And I'm not going to add in the hydrogens just for simplicity here. So the next thing we're going to do is it's this bond right there that's going to end up at the base. So as a result, we're going to kind of bend that bond up and that bond up. So as a result, here's carbon 1, carbon 2, 3, 4, and carbons 2 and 3 had their hydroxyl groups down, and then at here's carbon 5, and there's carbon 6. Now, this is a D sugar, and we know that because the hydroxyl group at carbon 5 is on the right-hand side. So in D sugars, we expect that in our final structure, carbon 6 is going to be pointing up this way. That's to get the correct stereochemistry at carbon 5. So essentially what we're going to do is we're going to rotate. I'm sorry, in this structure I forgot to draw carbon 4. So we're going to rotate so that this ends up over there. So let's go ahead and do that. So here's carbon 4, and carbon 4 has its hydroxyl pointing up, and then there's carbon 5, and there's the hydroxyl on carbon 5, and then there's carbon 6. Now all we have to do is basically have that hydroxyl attack the carbonyl, and that's going to form the cyclic structure. So we'll get now we're going to end up with a hydroxyl on carbon 1, and we can end up with two different possibilities. This would be our alpha anomer. The other possibility would be the beta anomer that would look like this. So beta and alpha would be the two possibilities that would form from this. So now we're going to do the same with a ketohexose. Ketohexoses tend to form furanoses. So a furanose is basically a 5-membered ring that looks like this. And essentially, we end up with carbon 1 and carbon 6 hanging off the molecule, and carbons 3 and 4 form the bond at the bottom of the structure. So once again, we're going to do the same thing that we did previously. We're going to rotate 90 degrees so that we end up with this. And once again, because the hydroxyl's on the right-hand side at carbon 5 in this case, this once again equals a D sugar. Now, carbons 3 and 4 are the ones at the bottom, so basically these carbons here, so we're gonna put those at the bottom of our molecule as we kind of bend things up. So so there's our carbonyl group, and carbon 3 has its hydroxyl up, carbon 4 is up as well. And then once again, we've got to rotate to allow that hydroxyl to ultimately attack that carbonyl. So basically, we're going to have carbons 3 and 4 right here. And then here's carbon 5, and the hydroxyl is going to be right there. That's going to be able to make that attack. And then carbon 6 will end up out there. And now we'll do our attack, form the ring, and once again, we're going to have two potential possibilities. We can form an alpha anomer or a beta anomer. So in both cases, the hydroxyl groups at carbons 3 and 4 are going to be pointing up. There's carbon 6. And then, so remember that the carbonyl group is what gives rise to the oxygen on the anomeric carbon. So if that hydroxyl is pointing down, this is the alpha anomer. Now we still have to take into account that there is carbon 1 still there. So that would be our alpha anomer. The beta anomer is simply going to look like this. And there's our beta anomer. So these next couple questions are going to look at going from a Haworth projection back to a Fisher projection. Generally, we don't do this too often, but this will hopefully give you a little bit of help in looking at the structure, or sometimes going in reverse can help you understand the relationship between the Haworth and the Fisher projection. So looking at this structure, basically, here's our anomeric carbon. So this is the bond that's going to break to open up that ring structure. So let's go ahead and draw what happens when we open our ring structure. So now we're going to have our aldehyde back. Now we just need to, so the other thing to consider is that because carbon 6 is pointing up, that tells us that the stereochemistry at carbon 5 is giving us a D sugar. So that means that carbon 5 hydroxyl should be on the right. So if we're going to have to essentially twist that bond around, and so here's carbon 5 right here, and as we twist that bond around, the hydroxyl is going to end up pointing down, Now what we're going to do is, when we went from Fisher to Haworth projection, we rotated 90 degrees clockwise. Now we're going to rotate 90 degrees counterclockwise. So as a result, everything that's on the bottom will end up on the right. Everything that was on the top will end up on the left. So we've got OH, OH, and we can add in the hydrogens there to complete the structure. So that's basically how we convert from a Haworth projection back to a Fisher projection. And of course I'm going to give you one that is a ketose. And once again, here's our anomeric carbon, so that's going to end up being the carbonyl group, the ketone. This is the bond that we're going to break in opening up the cyclic structure. So let's go ahead and do that. Oh, sorry. Now, in this case, it doesn't matter where we put the carbon-carbon double bond because there's no stereochemistry at that position. The only ones that matter are carbons 3, 4, and 5. Those are the three critical ones. Now, again, because carbon 6 is pointing up, that tells us the stereochemistry at carbon 5 is a D sugar, and therefore the C5 hydroxyl should be on the right in our Fisher projection. So basically if we kind of line this up, so there's carbon 2, carbon 3, carbon 4, and then carbon 5 is going to end up with its hydroxyl pointing down. And then we're going to rotate 90 degrees in a counterclockwise fashion. And add in our hydrogens. And there we have the Fisher projection from the corresponding Haworth projection.